Good morning. Today we are, mic on? Yeah, okay. So today we're solving the order of succession puzzle on codeandgame.com, which should teach us about graphs, pathfinding, and depth first search. I have some knowledge of DFS, depth first search, graphs and pathfinding, but I wouldn't say that I am, strong in that area. So this will be fun. Okay, so let's dive in. Our goal: you have to output the order of succession to the British throne of a list of given people. The order is simple. From a descendant A, the next in the order is A's first child, B. Then the next one is B's first child, C, as we can see here, if any, and so on. If C has no child, which I believe in a graph is called, or in a tree is called a leaf. So if C has no child, then the next one is B's second child. So we go back up and we take the second one, which would be D. Then D's children, if any. Then B's third child. Then A's second child. Yeah. Okay. Let's draw it with a tree. You see the order of succession. Begin on the left of the tree. So if we're using indexes, it would be, index 0. Walk to the next level whenever possible, otherwise continue to the right. Repeat until the whole tree is covered. And we can probably use some kind of recursive function here if the tree is not too deep, because we're using JavaScript. There's no tail recursion optimization really, so we can load a stack if the tree is too deep, but we'll see. Okay, so repeat until the whole tree is covered. In fact, in siblings of the same person, the male descendants are ordered before the female descendants. For example, if the order of birth of the children M for male or F for female is FA, MA, ME, FE, then the order of succession in these siblings is MA, ME, FA, FE. Okay. So I guess we're going to be given the sex of each possible candidate. Ordering rules. First, in order of generation, which is what this describes here, I believe. B, in order of gender. We'll see about that. C, in order of age. Okay, year of birth. Outputting rules: exclude dead people and exclude people who are Catholic, but include siblings of Catholic people. Okay. See, this here would have been pretty simple. Adding this is going to make it interesting. Let's take a look at our inputs and outputs here. Oh yeah, okay. So line 1 is the number of people, n, which I don't really know why that would be relevant, but whatever. Next, n lines. Oh yeah, to know how many lines we need to loop for. Okay. Name, parent, year of birth, year of death, religion, gender. If the people is not dead, then the year of death is replaced by the hyphen. If the people is not dead. Okay. One name per line in the order of succession to the throne. First the queen, then all her descendants. Exactly one people does not have a parent. The parent's name is replaced by the hyphen. What? How can someone not have a parent in the tree? Okay, basically our root. No two siblings of the same gender of a person have the same year of birth. No two siblings of the same gender of a person have the same year of birth. So there's no twins, is what I am understanding. There's no twins of the same gender. Okay. Okay. So if we're looking at this example input, 6 is the amount of people in the graph, in the tree. It's a tree. Elizabeth is the name of the person. It has no parent, thus the hyphen. She was born in 1926. She's still alive. She's Anglican, and she's female. Okay. Then Charles, parent is Elizabeth, born in 1948, still alive, Anglican, male. Then William, parent Charles, born 1982. 1982, yeah, okay. Still alive, Anglican, male. Then George, born 2013, Anglican, male. Charlotte, they're both children of William. And then there's Henry. Okay. So we need to construct the graph? I'm wondering, because we're being given that information in, is it in order of age? Generation, male, female, younger age. It's not evident with this test case. Let's take a full Elizabeth tree to get a better idea of what we're getting here. Andrew. Where's Andrew? Andrew. Okay. 1960. Charlotte William. Henry Charles. They're all Anglican. Interesting. So I was thinking that we would need to construct the tree. But I don't know. And then afterwards, do some kind of search on the tree. But I'm wondering if we can't just do that as we're taking in the inputs, basically. Maybe. Okay, we'll see. Let's get some of our instructions here. Just to help us. Oh yeah, that was dumb. Let's just do that. Okay. Don't need this. Oh yeah, as usual, we need to tell TypeScript about, let's just put that here, about the readline function, declare function, readline, put string, okay, because readline is a built-in function in the coding game engine that TypeScript doesn't know about. Now it does. Okay. So this is code that's already written for us. This kind of starter code, like that. So what are we doing? We're getting the first line, which is the number of people, hence the number of lines. And now we're looping for that amount of lines, that number of lines, and we're getting our inputs. Name, parent, birth, death, religion, etc. etc. Okay, so I'm just gonna... I'm thinking that there might be a way to actually not have to build our own tree data structure and just basically do whatever kind of logic we need to do inside that loop as we're going through each line of the inputs. But for now, I will build my own tree data structure and put everything in there. And maybe I'll refactor it afterwards if I find out that it can be simplified. So for starters, I'm actually going to make a class that we're going to call person. And the class is going to take a constructor. That constructor is going to take, how many inputs do we have here? 1, 2, 3, 4, 5, 6 inputs. Ugh. Should really pass that in as an object, I guess, then. So that's what I'm going to do. And we're going to call that, person, what would you call that? Name, parent, birth, religion, gender, person, parameters, I guess. That is an object of type. I'm going to take a name, it's going to be a string. Actually, how about I just, because I have a feeling I'm going to, oh, this is actually, this is going to be a node in our tree, right? So let's call it person node. And let's make a type. We're just going to call that person param maters. And okay, let's take this here. Yeah, let's just type it in. Name, type string, parent, type string. Oops. Birth, type string, they're all strings. Death, string. Religion, string. And gender. Actually, gender, we can do this. Let's see. It's either a male or a female. You can actually type that. Person parameters is of type person parameters. How's that? Huh? Now, oops. Do we want to start by, I'm actually going to put that at the top. Keep our logic here. Okay, now as we're going through each of those, so actually logically parent should take a person node, right? We're gonna we're going to not put the string, but we're actually going to try to tie in. And this is where our tree structure is going to be happening. Okay, this we could keep as a string. This we really just need to know if they're alive or dead. So maybe we simplify this and just go alive is alive. There we go. Let's make that a Boolean. So we don't really care what their birth date and all that is. Religion, again, we don't really care to display it. All we need to know is do we need to know if they're Anglican or do we need to know if they're Catholic? Is, well, whatever. Is Anglican. Is Anglican. Boolean. Because we don't like them Catholics. I'm not saying that. I'm just, that's the order of succession thing here. Exclude people who are Catholic. But include their siblings. No, include siblings of Catholic people. Yeah. Oh. Siblings, not children. So that means that we just, okay. I think I understand, but we'll see as we go through this. All right. I think this gives us what we need. So here, we'll start by making a our new person node. We're going to pass in an object that has a name parameter of name. And, well, actually I can just use this. Oh, you know what? Okay. This will be, I'll make all that work inside our constructor. And I'm actually going to just go like that. So new person node is just going to take in an object, and it'll be really easy because I can just use object deconstruction here and just go like this. Parent, birth, death, birth. What's wrong here? The type number is not assignable to type string. Why would you parse it in as a, who cares, right? Oh no, we do need it because we need older people or, yeah, okay, yeah. This number. We need to take into account, I forgot about that, we need to take into account the age of each person. Okay, so there. Birth, death, religion. Religion and gender. Gender type string is not assignable to type M or F. Yes, I know. Okay, fine. There. Okay, and now in our constructor we can deal with that and make what we're really interested in is name. That's going to be a string. Can I use this? Yes. Then, sorry. Yeah, take it easy. We'll deal with that. Our parent is going, oh, here, string. Interesting how it doesn't complain about that. Whatever. Here it's going to be a person node. And birth, we're going to keep keep that as a number. And here we're going to go is alive, Boolean, oops, Boolean, and is Anglican. It's going to be a Boolean, and gender. Here I'm going to type it the way I wanted to type it before, and oops, female. Now I can do this dot name. This dot name is equal to person parameters dot name. Good. This dot parent. Okay, so how am I going to do this? I need to somehow traverse the tree, find a person node that is the parent, and then okay, I'll get back to this one. Birth. Actually, we're interested in age, aren't we? So how about we do age? We can just keep birth. We'll just compare. Comes to the same thing, really. Birth. So this dot birth equals person parameters dot birth. Sorry. This dot is alive is equal to, let's see, let's just do this then. If person parameters could I just make this a ternary? Yeah, I think I will. I usually don't like doing that, but is equal to, now we're checking person parameters, equals, what was it, just a hyphen, I think, if the person was dead. Let's take a look at this. Yep. Person parameters dot dead. If it's that, they're alive, and I can just output true, otherwise false. Okay, and this dot is Anglican. We'll use the same kind of syntax here. We'll use religion. If religion is equal to, how do they spell this? With a capital uppercase A. So if it's Anglican, you return true. Otherwise, you return false. Okay. I haven't misspelled here. Gender. This dot gender is equal to person parameters dot gender. As either M or F. We know we're not going to have a problem with this, so just coerce the type. And now, how do we deal with parent? How do we deal with parent? Well, we need a way to find the person node that is the parent by using the name. So we'll make a method called find by name. Should I make a separate tree class? That would be better. That's what we're going to do. Class tree. Let's call it person tree, I guess. And it's going to take in a root node. So let's do constructor, right? Root node. We're going to need to access this. I don't think we will, so let's make that private. Private root node. And it's going to be a type person node. Okay. And then we'll have our method find by name, which will return a person node. Person node. So it's going to need to start at the tree root. So it's going to be a for loop. No, maybe a let's see, for we can probably use recursion. So I need to get, okay, let's just do this in pseudocode for now. So I need to get leaves, right? Not leaves, or what are they called? Branches? No. Children. Yeah, that's the correct. Get children. Okay. So I need to get the children. And this is where the okay, I get children. Oh, first actually I need to check the root. Right? So get node. How does that work if I start with the root node? Find by name. So this, I would do this root node. I think we can do a recursive function here. So it's called node. No, it's kind of dumb. We already have what we need. Don't need to pass it in. Although we need a place to store it. So current node. That's going to be a let. Let current node equals this dot root node. Okay. And then we check if current node dot name is equal to, okay, find by name. We need to pass in the name, so name. Boop, 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 boop. Mistake. So name type string. Alright, so if current name is equal to name, then we're done. Just return. Yeah, return the current node. That's the one we're looking for. That's our stopping condition. But if that is not the case, we need to get the children. So get children. I'll work on that after that. Get children. Okay. Then for each children, for each children, no, I do need to have this as a param, but let's see, current node, because if I'm going to do this recursively, I need it there. Current node is equal to this dot root node. Okay. Current node, did you mean current node? Cannot find name current node. Did you mean current? No, I didn't write it properly. Current node, okay. Then for each children, you call find by name, passing the children as the current node, which will check if it's the one we're looking for, and we'll check if it has children, and Yes, I think that makes sense. I think that makes sense. I'm wondering if yeah, okay, let's do that. So get children. This shouldn't be too hard. We just go current node. So our person node needs to have also a children array, which is an array of person node, and it can be empty if there's no children. And when we are constructing it, we don't know what the children are yet. We're basically going through each person and putting them in the appropriate parent. Yeah, that works. Okay. So current node, that children. Well, so I guess I don't really need to get it. It's simple for loop here. For const child of current node children. If it's empty, what's it going to do? It's going to do nothing, I think. I don't know what the behavior of a for loop when you're trying to iterate on an empty array. We'll find out, I guess. So for each child of current node, we just recursively call this .find name by, we're passing in the same name, we're looking for the same person, but the current node now becomes the child. And that should be, oh, we need to return this. Return this. No? Why? Why are we not, lax ending return statement? Okay. If current node dot name equals name, then return the current node. That's our stopping behavior for const child of current node children. Find this by now. Okay, but what if we do all of that and then we don't find anything? Right. Such as when we're doing our well, then we return the root node, or just the current node, I guess. Does that make sense? Either way. It's its own parent, basically. Yeah, I think it'll work for what we need to do. Okay, now that we have this. No, that doesn't really make any sense at all. I'm calling this, so let's say I'm calling this with an unknown name and we only have the root node. So it's checking this, no, skipping that. For child, there's no child, so it's skipping that. Then it gets to this. What do? We return the current node. Probably should throw, is what I'm thinking. Or just return a null. What if I were to throw? How would that throw? Yeah, just throw a new error. No such name. Of course, this screws the type. It works though. I could make like a null object. I could make a null person node. I've never actually used the null object pattern before, and this would be an interesting place to use it. And since I'm here to learn, let's do that. There's this nice little website I like to use for design patterns, and it's called Refactoring Guru. Design patterns, creational, I think, maybe? No? Structural? No? Behavioral? I don't think so. That wouldn't make sense. Oh, so they might not have anything about the null object pattern in here, which really surprises me. Is there a way to search that site? Nope. Let's use Google Refactoring Guru null object. Oh, it's talking about it. Okay, it doesn't have it as a pattern per se, but it talks about it in their refactorings. Problem. Since some methods return null instead of real objects, which is what I would be tempted to do, You have many checks for null in your code. Instead of null, return a null object that exhibits the default behavior. Class null customer extends customer. That's basically just it, and then boolean is null, return true, plan, get plan, return. Replace null values with null object. So now instead of doing a check for null, customer equals order the customer, new null customer. Okay, this is what we're use null object as if it's normal sub plan customer that get plan, return new null plan. Okay. Order the customer or new customer. Interesting. Not too complicated, except I have to do a null person node. It's definitely overkill here, but just as a learning thing, let's do it. Null person node extends person node. Node, and then use before its declaration class person node. Oh yeah, am I doing that? Eh? I am doing that, aren't I? And if I'm looking at our example here, I have to, actually I don't have to do much. I just have to return a well, if I was to just create a person with no, I don't think that works, because if I do that, I'll just return null for that. For now, anyways. Okay, now. Because really throwing an exception here doesn't make sense. I'm thinking because the find by name, we're trying to find something, we may not find it, it's a possibility, right? So it's not throwing an exception, doesn't make sense in that kind of method. So what do? Well, you return null. That's what I'm doing. Okay, now the whole purpose of doing this was that so we could, in our constructor, do oh, interesting. Now my person node needs to know about the person tree, which makes no sense. Well, I wouldn't say it makes no sense, but how do I want to do this? Would it make sense to make this static somehow? Well, we don't plan to, well. So I would do this, create, let's see, let's just call this const tree equals new person tree, pass in the root node, which we don't have. Okay, this is a problem. This is a problem. I can't do my tree without a root node, and now I'm setting things up so that my node needs to know about the tree. Grr. Circular dependencies, or whatever you call those. Okay, my problem here is that I'm trying to build a tree, and I want to hook up each node to the right parent, and I'm only getting that as a string, and I'm not sure the order is actually, I know the order is not right to just let's take a look at this again just to make sure that if we take a more complex case. So we're starting off with Elizabeth, then she has Charles, then Charles has William, then William has George, then William has Charlotte, then we go back to Charles, who has Henry, then we go back to Elizabeth, who has Andrew, then Andrew has Beatrice, and Andrew has Eugenie. Then we're back up to Elizabeth. Elizabeth has Edward. Edward has James. Edward has Louise. We're back up to Elizabeth. She has Anne. Anne has Peter. Peter has Savannah. Peter has Isla. And then Anne. We're back up to Anne. Anne has Sarah. Sarah's Maya. Okay. So it seems to be in order. It seems to be in order. But I don't very much like the fact that we're kind of, So like I was saying at the beginning, I think we might not need to construct our own tree and just basically do all of our logic straight in that loop here. Just going through each line. Might just try that. So let's put this on hold for now. This will just be a string again. Yeah. Okay. And in that case, we can just do we still have that children? We do. Okay. So what we could do here Yes, I don't know. I still think that it would be easier to reason about if we just have our own tree. Okay, let's try to figure this out. If I was to do something really simple and have, let's say, a simple data structure, const. Actually, we're starting off with a root, so okay, let's do that. Let root node equal just let's okay, root node is going to be an object, whatever. Okay, so we're starting off at first, so we're going to put we're going to make root node be, no, see, that still doesn't work. Still doesn't work. No, I think I'm going to use my tree because it'll be easier to reason about anyways. Cleaner. But now I have to fix the problem where I kind of need to know about the tree to create a person. Oh yeah, I can fix that. We'll just go if it's the first one, if I is equal 0. If I is equal to 0, and that's our root node. Let's create a root node. Oh, I know. We can just shove the tree in the constructor. Root node. That makes sense. Then I wouldn't really need a separate tree thing because I could have it right in there. Alright, let's just write this like parent person node. Well, do we actually need to know about the parent here? We don't. We really don't, do we? We don't need to know about the person node, the parent node, in the person node class. So let's just get rid of it altogether. And that way we're able to construct our node. And then we'll just use that, the tree, to plug it in wherever it belongs. So we'll call that add node. It's going to take in a person node. Person node. Okay. Just going to look for person node. Okay, so we still need it. We still need the parent. As a string though. Just as a string. Parent is equal to person parameters dot parent. Okay. Dot name. So once you find it, no, not by name, the parent. Right, so we want to add this node here. Well, what's this node's parent's name? We find that node, and then we simply, so this would be const. Well, actually I can just do dot children dot push person node. Simple as that. Or maybe not. Seems to be a problem. The object is possibly null. Which one? This one? This one? Which one? This one? Yeah, person node dot parent. The result of this. Okay. So if, okay, so let's start by finding our parent. And then if there is a parent, here's what we want to do. Oops, already had it. Okay, so we're good with that.
1, 2, 3, 4.
So let's try this now. We will let root, or let's just call it tree, let tree, let person tree equal, actually nothing, let's just make it a type person tree. So if I is equal to 0, then 3. Yeah, okay. Let's do it that way. It's got to be a let. Person tree is equal to, no, it's of type. Person tree. Like that for now. Oh, I had put it, let's just put it in here. So if is equal to, okay, so we create our new const root node. Is equal new person node. And we just pass in an object that has the name, parent, birth, death, religion, and gender. Okay. And then we just create our tree. So person tree equals new person tree, pass in our root node. There we go, we're in business. And then for all the other ones, we take our person tree, we go add node, and we take, oh, we need to create a so we can actually just go const person node, person node, take that out of here, put it here, and then just go person node. Yeah, person tree is used before being assigned. It is? No, it's not. How is it? No, because you don't know. You know what? This would all be easier if that kind of logic would be straight in the tree. And we could just forget about the passing in this here. Const. What am I doing? Root node. Private. Private. Root node. Okay. Oh, this isn't any type. No, it doesn't. I'm gonna take care of that. Okay. There's no initializer. Is not definitely assigned in the constructor. That's true. But we're cool with that. We are kind of cool with that. So it can either be this or it can be null. Or undefined, maybe. Yeah. fix my problem with it. So if current node and current node.name is equal to name. So if current node might still not be, you didn't have to check. So we need to wrap this apparently into another if current node otherwise just return null. Oops. So if we do this, if there is a current node, we do that. We do that. If none of this happens, return null. If there's return null. Okay. And then here, add node. If there's no parent, if there is a parent, parent dot children dot push. No. If there is no parent, well, first, if this dot root node if there's no root node, very simple, just return and just this dot root node equals person node. Otherwise, find the parent. If you do find the parent, you push it. If there is no parent for some reason, well, this should throw an exception because it's not normal that we're trying to, yeah. So throw new error. No such parent in tree. Okay. So now we're going to just create our tree right here. New person tree. Okay. Why did I delete my node? Const person node equals new person node. Pass in this object, name, parent, death, religion, gender. What am I missing? Birth. Oh, birth. What? Birth, yeah. Okay. Let's put that in the right order. Name, parent, birth. Okay, and this should give us a tree. It's a start. Let's take a look at what we get when we do that. Person tree. Oh. Oh yeah, we didn't set up our external. We didn't set up our external ID. Let's do that. Order of succession. This one here. Okay, upload from local file to code and game. Good. So you can see this worked. Let's try that. No such parent in tree. Okay. Well, we are throwing our error, but I was kind of hoping that it wouldn't happen. Oh, we're not returning. We have to return here. Let's try that again. Okay. So we got our person tree that has a root node. That root node is a person node that has children that are person node. Oh, hold on. Name Charles, birth true, blah, 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 blah. Person node Charles. Okay, those are Charles' children. Am I wrong? Gender female. Name Charles. Birth 920. So this should be name Elizabeth. Okay, screwed something up in the way that I'm constructing our person. Thinking name equals person parameter dot name parent person parameters dot parent. Add node parent is fine by name person node dot parent. If parent return this. Parent dot children dot push. Person node. Hey, Chai Tai. Doing great. What about you? Find name. Name if current node. Current node dot name equals name. Return current node for const child of current node. Children. This shouldn't be a problem. So how are we getting? Pretty good. All right. Where are you from? A little bit of debugging here. To do though. I would have to replace all these inputs. Ugh. New Mexico. Right on. I'm in Canada. You just finished your mic classes? just finished your classes, okay. Getting back into rigging. Rigging what? Oh, okay. Rigging in 3D modeling. Very nice. So I'm guessing that you want to be working on games. It's ridiculously hard. Yeah. I've dabbled a little bit, and I agree. There's a lot of stuff to learn, but once you know the tooling and the techniques and all that, I think it's not necessarily all that hard. It's just getting there, you know? Getting the practice in and getting better at it. Okay, so what am I doing wrong here? It seems to me that I'm creating, this is my root tree, it's got a person, and that person is Charles, when it shouldn't be. It should be Elizabeth. And Charles is being, it has every, yeah, everything else is fine. This is Elizabeth's parameters, but for some reason, name is Charles. Well, I guess more finicky, you say. Yeah. Getting my stuff to transfer from Blender to Unity is annoying. Yeah, when you're working on games, well, not just games, but it's important to have a good kind of workflow with tools that work well for all that stuff, you know? When you want to push stuff from one tool to another, and if it's a hassle, it really slows you down. You need to figure that out and set all of that stuff up first so that everything is as seamless as possible. But that can be a pain. Name, person parameters, dot name. Is it name, input 0, parent, inputs 1, taking name from name. Let's do it here then. Let's do console of error, get our person node. There's the animate. Yeah, animating is another thing. I mean, 2D animating is hard enough. 3D as well. Actually, I think some may say that 3D animating can be easier than 2D, depending on the kind of animation you want to do. Like if you do by hand 2D animation, you have to really be a good artist. If you're using more like what do they call it? You know, like skeletal animation, where you just take a 2D drawing and it's basically build a skeleton, and then you can just move every little bone in the skeleton. That's a little easier to do, but it's a different look. Tempted to throw down an extra $300 to get a Kinect and program to just motion capture. Yeah. Well, I don't know how well that would work. Okay, let's see what happens if I do this. Name, Elizabeth. Oh, okay. So it's working. It's just, it was displaying it weird in my tree for some reason. Children. Okay, I think. Nope, that doesn't make any sense at all. Let's try something else. When you planning to finish this? Yeah. I was planning to finish this before 11, but it's not going the way I was thinking it was going to go. So I might have to finish this afternoon. Okay. Hey, thanks for the follow. Michigan Man 1019. So this is getting a little hard to read. I'm just curious what the output is for my find name function here. Children. Name Charles, birth 926. That's incorrect. His birth is 948. Male, female. So I screwed something up. Somehow instead of putting Elizabeth's name here, it's putting Charles' name. Why? Let's find out if we can. We are passing the right thing here, as far as I can tell. We're creating a new person node. No, person add node, person node. And here we're saying if there's no root node, then this root node becomes a person node, and you're done. Otherwise, parent, return parent.children.push, person node. I am perplexed. So let's take a look at person node dot name. Like that. Don't really care about that. We'll just leave it. Okay. Elizabeth, Charles, William, George. This is all working for some reason. Children. William, George, parent of William. I'm not sure we're doing this right, folks. It's kind of hard to see here, but might just be the way it's displayed though. What if I was gonna do person tree? Just for the sake of debugging, I'm gonna leave that as public. Person tree, root node, just like that. children, we have Charles, but this shouldn't be a children here. So there's definitely something not working here. If I add the node and it's if this root node, turn this root node equal person node, const parent equal this find by name. If parent return you return parent children dot push. So I think it's something that's going wrong in here. Let's take a look at, let's see what happens here. Here. Technically, this should, we should have one of these for each line except for the first one, for the root one. Person node, name Elizabeth as the parent, yes. Then we have Charles. How is Charles? How does he end up with 1926 as a birth date? And all of everyone ends up with that. Except when that is very weird. I don't get what's going on here. What is this thing returning? Person node. Let's check this out. If current node.name is equal to name, return the current node. This is a hard one to debug. Can't figure it out. And I thought this was going to be easy. Ha! But you know what? I am convinced that this isn't the way. To solve this. Anyways. So I'm just going to comment that out. Try to figure out how to do it. Right in here, which I'm willing to bet that's how they intend it to be done. Const, let's call it results. Make that an array of strings. Array of strings. Okay. So basically, what's an easy way to do this? We're going through the line. We're gonna get Elizabeth as the first one. So obviously she's the first one to get in there. If she's still alive. So if death, that's the first thing we need to check for. If death is equal to this, then and religion is equal to what was it, Anglican. Then we're good. You can just shove that in there. Results dot push. We just need the name. And what is the output that we're expected to feed to this thing? Well, line by line. Ah, interesting. So then we'll just go results that for each. Simply console log should work, right? Let's see if I get this right. Found. Oop, I'm still logging some stuff here that I don't want to log. Am I? Nope. It's odd. Let's run it again, see what we get. Let's run this. Okay. What am I doing here? Results dot push. I'm just pushing the name. It's weird. It's just console.log. Our entire results array, which should be short anyways. Okay. So really, I guess it was something wrong with the way I was doing results dot for each. Yeah, this should work though. Whatever. So name console.log name. See what that gives us. There we go. Okay. But of course this is gonna work. Oh, okay. Dead people. Dead people. What seems to be the problem with the dead people? Prince Andrew, Duke of York. And we found Prince Edward, Earl of Wessex. Prince Andrew, Duke of York. Expected that, and instead we got Edward. Okay, let's take a look at that test case. This is what we're getting. Just get rid of that. Shove that in there. And expected output right here. Oh, I must be missing something here. Arthur Chateau, Queen Elizabeth II. Okay. King George, Queen Elizabeth II. He's dead, so we're not using him. Good. So we're doing fine until we get to Prince Edward, Earl of Wessex. Prince Edward, Earl of Wessex, here. And they were expected instead Andrew, Duke of York, which I have in the reverse order. Why? Prince Edward is older. That is why. That is why this dude needs to come first. How do I deal with that? Is what I wonder. Well, we need to somehow store siblings and order them by age. Right, they both have the same parent. How do I detect that in a non-complicated way? Okay, I'll just use this. Const parent. No, we'll just actually let parent equals whatever. We'll just, it's just going to be a string. All right. Do I have? Oh, I've got this here. Cached parent. How's that? Cached parent. And then we'll have an array of siblings. Let siblings okay, So, first thing we need to check is, do we have a new parent here? If, oh, that's still not going to work. Because they're not in order. We go down the tree first. It would work if it was breadth first search, but it's depth first search. How do I deal with that without building my own tree? Do I have to? This is really screwed up because they're feeding us line by line the tree, right? And it's somewhat, well, it is depth first, kind of, right? We're starting with, let's see, so King George had Queen Elizabeth, cool. And Queen Elizabeth had Charles. Then Charles had Prince William. And Prince William had Prince George. And then Prince George is way too young to have his own kids. So we're at the bottom, we're at the end, we're at the leaf in our tree. So what do? We go back up one level to Prince William, and he had another kid, Charlotte. Cool. Charlotte doesn't have any kids, so that's another leaf. We go back up to Prince William. Prince William doesn't have any other kids, so we go back up to Charles. Charles had another kid, Henry, Prince Henry. Henry doesn't have any kids, so we go back up to Prince Charles, which doesn't have any other kids, so we go back up to Queen Elizabeth. Now the problem is that apparently they're not feeding this in necessarily in date of birth order, as you can see. So we're back up to Queen Elizabeth, which had another kid, Edward, in 1964. Apparently Edward doesn't have any kids, so we go back up to Queen Elizabeth, which had another kid, Andrew. But Andrew was born in 1960. For some reason, they don't give us, they don't give them, you know, we're not being fed that information in order of year of birth. So how do I deal with that? How do I deal with that without having to build an entire tree myself? Which seems like kind of dumb because we're being fed this information in a tree-like way. Kind of. All I really want to do is change the order, because up until now the succession order is as it's coming in, but here it's not. So we need to fix that. How do I? And the rest too is probably going to be impacted by. Oh no, not really. As long as we. Oh yeah. So it would have to be Prince Andrew, Duke of York, then his children and his children's children before we even get to Prince Edward, Earl of Wessex. I really don't see a way to do this without actually building our own tree. I really don't. So let's comment that out. But let's try to make it simple, really, and just get the two informations that we really need. Actually, we're not going to comment that out, because if someone's dead, Oh no. If they're dead, we still count that they're not part of the succession, but their children maybe. Okay. As is the case with, for instance, George. George is dead, but Queen Elizabeth is alive, so she's part of it. Okay. So, we do need some sort of data structure. We need to replicate this. Let's just try to make it simple. So let tree. It's going to be an object. I don't know what kind, how I'm going to do it for now. Let's just try to see, reason through this. We're getting Elizabeth as a first. No, we're getting King George. So King George is our root. So let's put King George in there. So tree equals, and let's make this see, name, and what else do we need to know? We need to know if they're dead. Also, we need birth. What else do we need to do? We need everything, really. So we're back to our original, my original idea of using, which I have deleted. Sweet. Brilliant. I'm pretty sure I can Control Z my way back to that code. Check this out. There we go. Up. Okay, but I know that I have a bug in here. So what I'm going to do is probably try to reason about this some other way. The node is fine. I don't see anything wrong with this, right? Person parameters. The name becomes the person parameters name, the birth, no. It's all good. This is all good. So what I need to do, and we have children, yes. So let's just do this. Let tree. It's going to be of type person node. Try to keep it simple. Still comment that out for now. Okay, don't need you. So we're creating a new node. Right, so our tree is equal to new node, person node, and we pass in all those parameters. Parent. Spent the past 2 hours just going back and forth between trying this out and something else, some other solution, but always come back to this. So, all right, now we've got our root node. Now what? Well, we need to add children. That's what we need to do. Because if I just keep that in the loop, it's just going to continuously replace the root node. So I do need some method to add children. Well, I could, let's see. back to the same problem because we're being fed that information. How do I keep to the same level? Alright, so we do know that we need a method to add children. Unless we we could always keep it simple and just push straight to keep it public. Yeah, let's do that for now. Alright, so let's say that we know that this is the root, this is the first one. So just go ahead and create our tree. All right, just go ahead and create our tree. But if it isn't the first one, then what we want to do is actually add children. Right? But now, wait a minute. At some point, we need to go deeper. And therein lies the problem. Therein lies the problem. If I was to gonna have to think about this some more. And I'm running out of time, so I think I'm just gonna end things here for this morning. Think about it some more, and hopefully this afternoon come back with a solution that'll work. Yep, I think I'm close to, but it's just something that's escaping me. Okay. Got this here, I'm good. Okay. This I'm pretty sure I'll be using. I don't see any other way around actually building our own tree and then having some sort of search down our tree that takes into account the date, the birth year, and the fact that we're alive or not. And yep. Okay. All right. So I guess I'll be finishing this afternoon. Thanks for sticking around, those of you that are still there. If anyone's still there, maybe I'm just alone. And I'll see you tomorrow with another puzzle, possibly. Take care.